The second speaker of today is Moeller, and he's gonna talk. His talk title is A Geometric Classification of the Holomorphic Vertex Operator Algebras of Central Charge 24. You can go ahead.
Yeah, thank you for the introduction, Chiara, and also, yeah, I'm very happy to be in Rio. Yeah, I've been meaning to come here for a long time, and finally it worked. And I think this is a good occasion to talk a little bit about things that I did with a number of people, including the main organizer, Jethro. So this is something we've worked on for the last couple of years, and I think now we're kind of close to a completion of this. And it concerns the classification of holomorphic vertex operator algebras of central charge 24. So we are in this what Terry calls 20th century vertex algebras. And actually, this problem goes back to a conjecture by some proof, or some physics paper by Heluani in '93, and he proposed a complete classification of what he called meromorphic conformal field theories in central charge 24, yeah, so this has been done or approached from a vertex operator algebra side, and maybe one of the motivations to study this problem comes from the original moonshine business. So you have the moonshine module, or the monster VOA, and it's a very old conjecture to ask, is this the unique holomorphic VOA in central charge 24 that has a vanishing weight 1 space? And this question is still open, by the way. So this is still open. But then somehow people started to work on this adjacent problem of not just looking at this particular one, but also at the genus. There's a certain notion of genus, and Moreau, for example, gave some definition of a genus, and or Gerald Höhn, and in some sense, this classification that we're looking at is to classify all of the VOAs that have the same modular tensor category, which in this case is trivial, and the same central charge. So this is one of the motivations of this. All right. So I start with an introduction, which is completely unrelated to vertex algebras. It's just about lattices, but it turns out that we can generalize a very nice lattice result. So very nice classical result that goes back to Conway, Parker, and Sloan, and also to Borchardt. On the level of VOAs, and then you can see, so you see here, even though the VOAs in the end we are talking about are not lattice VOAs, but we still have enough of this classical structure shining through, just enough to be able to give a nice classification here in terms of, in the end it will be geometric objects in the Leech lattice. Yeah? So these are, in that sense, you're not, this is not something that Terry would call exotic, because you still have, even though these constructions are a little bit complicated, but in the end, it turns out that you still have enough of this classical stuff shining through to give you like as an organizing principle. And everything I say here is very special to central charge 24. Yeah? And okay, so for the lattices, this is something many people probably know, but if you consider lattices, so these are just free Z modules, and they have a quadratic form on them, or bilinear form. And we look at positive definite ones, even and unimodular. So unimodular is what corresponds to holomorphic on the VOA side. So this means that the dual lattice is equal to the lattice itself. And you can classify them in rank 24. And this is this famous Niemeyer. These are these famous Niemeyer lattices. And it turns out there are exactly 24 of these lattices up to isomorphism. And there were, and moreover, you can uniquely, if you want to give them a name, you can just look at the root sublattice, or the root system that's in these lattices. So you just look at all the vectors in the lattice that have length 2 or norm 2. They form a root system, and it's enough to look at this root system. It uniquely determines the lattice. And yeah, these root systems, you have some kind of ADE type of classification. That's why the picture is here. And then there's one special one, which is the Leech lattice, which has vanishing root system. So in this case, it has no norm 2 vectors. And so, yeah, in fact, the Leech lattice is the unique, unique unimodular positive definite even lattice in rank 24, which has no norm 2 vectors. All right. so this is a well-known theorem, and there are actually many ways to prove this. So originally, Niemeyer used Kneser's neighborhood method. So Kneser was his PhD advisor. He proved that if you have to define what a lattice neighbor is. It means you go to a finite index sublattice and you extend it again. And in fact, you just look at index 2 sublattices and you extend again to get another unimodular lattice. This is a neighbor. And he proved that if you have the lattice in a genus, if you go from neighbor to neighbor to neighbor and you do this, then you get all of them. So the neighborhood graph has just one connected component. So that of course means that if you're brave enough to sit down and compute all these neighbors and you do this long enough, you will get all of them. And that's how Niemeyer proved it. And then there are other approaches. Venkov gave a very nice proof using harmonic theta functions. I'll skip the third one for a second and come back to it. So then you can also prove it using the Smith-Minkowski-Siegel mass formula. This was essentially, this you can find in a paper by Conway and Sloan as well. And then very recently to French mathematicians Chenevier and Lannes, they gave a completely different proof using automorphic representations of O24. And now the third one is the one I want to focus on because that's the one we're going to generalize. And I will not tell you the story in the historical order, but so in 85, Borcherds actually in his PhD thesis gave a very nice, very short, it's half a page essentially, very nice proof that the Niemeyer lattices are in one-to-one correspondence with certain objects in the Leech lattice, namely dipoles. And how could he see this? Well, he had to actually go, he had to tensor everything. So you have your signature is 24,0. You have 24-dimensional positive definite bilinear form, and you tensor with something that's signature 1,1. So you end up with a Lorentzian lattice of signature 25,1, and in fact, all of the Niemeyer lattices, if you tensor with what's called the hyperbolic plane, so the unimodular lattice of signature 1,1, they all become isomorphic. They become the same. So there's only one unique lattice in unimodular lattice in signature 25,1. And if you embed into this, it's a very nice argument. It's completely conceptual. It doesn't need any kind of strange computations. Borcherds could prove that this is nice one-to-one correspondence. And then already 3 years earlier, Conway, Parker, and Sloan had classified these dipoles. They had already observed this one-to-one correspondence, but they couldn't give a conceptual explanation of this, and this was done by Borcherds a little bit later. Yeah? So well, I essentially already said it, but so what is a dipole? In general, if you have a lattice, so lattice is a free Z model. So you have this discrete substructure of let's say Euclidean vector space. You can take any basis of Euclidean vector space. You look at the Z span of this. This will be a lattice. Yeah, and then you can wonder what points or what are points that have maximal distance to the lattice points. Yeah? There will always be such holes in a positive definite lattice. And if it's not just a local maximum, but it's a global maximum, we call them dipoles. Okay, so that are dipoles. So then Borcherds proved that, first of all, he gave a very simple, quite simple argument that there's a unique Niemeyer lattice without roots. So that's the first kind of step you have to do. So then you can identify the Leech lattice. Now you have the Leech lattice, and then once you have the Leech lattice, you can prove that there is a natural bijection between orbits of these dipoles. There are exactly 23 classes of dipoles under this. So O of lambda is the orthogonal group of the lattice. So these are just the orthogonal maps that preserve the underlying ambient vector space that preserve the lattice as a set, and then you can also just translate by the lattice. And under this action, you have exactly 23 classes, and they are in one-to-one correspondence with the Niemeyer lattice. However, to prove this bijection, he didn't need to classify them. Yeah, that's completely independent of the classification. And then you look at the classification of these dipoles. This is now a very manageable problem because you just have to classify these dipoles. Yeah? I will explain a little bit how you do this at the end because we have to generalize this in any case. but that's something you can, that's something very manageable, and you get some kind of a graph problem. You have to start with, some point close to the origin, and then you have to make sure it has certain distance from other points in the lattice, and you kind of work your way through like this. And this is this is what I mean by classifying whole diagrams. I'll explain what these are. But this is very nice, and you can draw nice pictures, and all of this can be done by hand, which is quite amazing. And that gives you an independent proof of the Niemeyer's classification, and to me this is the most beautiful proof, because in the end, all of this you can do by hand, and you can write it on a few, maybe on 5 pages, while Niemeyer's proof, of course, he also did it by hand, but it's hundreds of pages in the end, because you have to go through many steps. And also, anyway, and this is the proof we want to generalize to vertex algebras. All right. Now let's come to vertex algebras. So it turns out that if you want to classify, now we're looking at nice vertex algebras, so that means strongly rational, or people have used different words for this, and there should be holomorphic. So nice is just a technical assumption in a sense, but holomorphic really means that the modular tensor category that's attached to your VOA as a module category is the trivial one. You have only one irreducible module, and in other words, every module is just copies of the VOA itself. All right, and then you realize that this is quite similar when you study examples of small central charge, and you realize this is actually quite similar to the lattice classification. Yeah? So the central charge here must be a multiple of 8. That follows from Jou's modular invariance result, because you have only one character, it must be modular invariant. Yeah? So the vector valued representation collapses to just one character. And then you look at central charge 8, and you only get E8 lattice vertex algebra. You look at central charge 16, you only get E8 squared, and you get D16 plus. Again, it just copies the lattice classification. But then in central charge 24, you get more. The moonshine module is a non-lattice vertex algebra. Okay, so then you definitely know you're getting more than just lattice cases. But still, somehow, it still mirrors this to a certain extent. And for the lattices, we wanted to look at the root system, and now we look at the weight 1 subspace. So of course, these nice vertex algebras, they have the graded vector space, and the 0 component is just the vacuum, and then you have the weight 1 component is the first non-trivial one, and that's always a Lie algebra if you have a CFT type vertex algebra. It's always a Lie algebra, and in this case, it must be finite dimensional Lie algebra. And it turns out it must be actually almost always, in this setting, almost always a semi-simple one. Could also be abelian. So let's say a reductive Lie algebra. All right. And that's a general proof by Dong and Mason that if you have a nice vertex algebra, then this Lie algebra must be reductive. And then Schelikens showed that he gave an upper bound for the possible way Lie algebra structures, and it actually more than just a Lie algebra. Also, anyway, he gave an upper bound for the possible Lie algebras that can appear in this weight 1 space, and he gave a list of exactly 71. 24 of them are lattice cases. One of them is 0, that corresponds to the moonshine module, and then there are more. And then he conjectured that all of these can be actually realized as vertex algebras, as weight 1 spaces of conformal field theories, or vertex algebras. And moreover, that if you fix a Lie algebra, then there will be only one vertex algebra having this Lie algebra structure. And quite amazingly, it turns out this is true, except for the one case where we don't know which is the moonshine module. But by the works of many people over the past 30 years, it was actually proved that this is a theorem. So there are exactly 70 nice holomorphic vertex operator algebras, central charge 24. We have to say with non-vanishing weight 1 space, and they're labeled by the weight 1 structure. So if you take a weight 1 structure from Schelikens' list, you can find such a VOA, and you can find exactly one such VOA. There is, of course, the example of the moonshine module for the 0 weight 1 Lie algebra, but it's not known whether it's the only one. Okay, up to 5 years ago, so let's say maybe 4 or 5 years ago, this was proved, but this was done mostly in a case-by-case approach, using orbifold constructions, starting from lattice VOAs, framed constructions, and things like this. but it was a mess, to be honest. So we had this theorem was known, but it was mostly a mess, and it didn't look like there was any kind of nice structure here. And yeah, one goal. So the goal of this talk is to summarize progress that was made in the last 5 years on a uniform description of this. So give a uniform proof of this result, and ideally, yeah. And in this case, it will be one that generalizes this very nice result by Borcherds and Conway, Parker, and Sloan, which is what they call the holy construction of the Niemeyer lattices from the Leech lattice. All right, and yes, so specifically want to prove such by a bijection to certain nice geometric objects which are much more manageable. Yeah? And this is based on several joint works. And I mean, first I have to say maybe the very first paper that appeared where such a uniform approach was studied was by Höhn in 2017. It's a very nice paper, but he uses a slightly different approach. He uses a coset construction essentially. So he in a sense he generalizes the concept of a Cartan subalgebra to vertex algebras and uses that to study. And he doesn't give a complete classification, but it's 95% there, and then for a few cases he couldn't prove the uniqueness. But in principle, with this approach, you can prove everything. But this is a slightly different approach, and I will not talk about this today. So today I want to talk. So as I said, I want to prove a bijection to certain objects that we call generalized dipoles, and they're in the Leech lattice vertex algebra. And so this map, we have this map which is just given by the orbifold construction. Cyclic orbifold construction. I will tell you what it is. And then you have to prove that this map is surjective, that is injective, and then finally use it to classify it. So then we just copy. This would be then on a structural level, just copy what Conway, Parker, and Sloan did, and Borcherds. And yeah, I think for the proof of the surjectivity, it was Jethro's idea to use this very strange formula by Katz, which I'm still amazed by the fact that so we had some combinatorial data from the VOA side. So we had proved the dimension formula in a kind of more ad hoc approach for genus 0 and using expansion of Hauptmodulen. And we saw based on that we could conjecture a formula, a general form of a formula. And there are certain coefficients appeared that, some rational numbers. And then just by somehow you realize that the same coefficients also appeared in what Katz calls very strange formula, which has to do with representation theory of in the end, affine Katz-Moody Lie algebras, and and by combining this, suddenly everything fell into place. Then we could prove a surjectivity. To prove the injectivity, it's a little bit harder. You have to take Katz's very strange formula and average it, and then finally, then you have this bijection, and then finally, recently, Scheithauer and myself, we've been working on using this to classify the VOAs, so then really just giving a classification of these generalized dipoles using generalized hole diagrams, and that we recently put on the archive. Okay, so that's kind of the things I want to talk about. Okay, so that was just the introduction. Yeah, so now you know what to expect. Okay, I don't need to define vertex operator algebras. So in the setting here, the grading will always start at 0 because they're nice and they have CFT type, and the spaces are finite dimensional, the weight spaces, and so you have this infinity of algebra products which come from, satisfying some generalized associativity and commutativity constraints, and which are originally motivated from I guess the Whiteman axioms of two-dimensional conformal field theory. And of course, recently we know that they can also be used to describe four-dimensional conformal field theories, and looking forward, this might be actually much more interesting development. But still, if you want to advertise VOAs, I think somehow you can argue that if you want to construct the monster group from first principles, you really have to use VOAs. You can Grice's construction is very nice, but he had to know already what the monster was to construct it. Yeah? But if you just construct the moonshine module from the Leech lattice VOA by an orbifold of order 2, you know nothing about the monster, and it just turns out that the monster is the automorphism group of this. So this is, to me, it's the only construction of the monster group that doesn't actually know what the monster is. Anyway, so that's yeah, and then the characters in this setting will be modular forms, and I will use modular forms a lot. So 90% of the proof of this result are using modular forms, vector-valued modular forms in particular. And so the one result I have to recall is and that's a very special case of what Terry was talking about last week. You start with holomorphic vertex operator algebra. It has trivial representation theory, so just one irreducible module. And you take an automorphism, and here you just take a cyclic group of automorphisms, just generated by one automorphism of finite order. In a sense, that's the easiest case you can consider. And then you can find out that the fixed points VOA, it has exactly n squared irreducible modules. And this goes back to Miyamoto, Tanabe, and Dong and some people. And they're all simple currents. Yeah, so the fusion rules are governed by an abelian group, and in fact, I mean, we know from this conjecture by Dijkgraaf, Waffer, Verlinde that we expect this to be the twisted group double of Zn of the cyclic group here, and I guess the main work was to identify what is the corresponding 3-cocycle that governs this modular tensor category. And it turns out it's just determined by the conformal weight of the twisted module, which is part of the modular data. Yeah? Okay, and anyway, so we determined this, and then once you know this, you can start to extend it again, and that's what's called the orbifold construction. So you go to the smaller object, which is the fixed point VOA, and then you extend again to something that's holomorphic again. And this completely mirrors neighborhood for lattices. Yeah, you go to some, in a sense, finite index sub-object. I mean, finite index doesn't make sense, but that's what you do. And then you extend again by some. It's a simple current extension here. Yeah? And because we have order n, it generalizes the idea of n neighbors for lattices. Okay. So to sum up, you start with the holomorphic VOA and you get another one. And what you put in is a holomorphic VOA and you put in an automorphism. Okay, so that's this cyclic orbifold construction. And so that's going to be our method for constructing those. Starting from the Leech lattice VOA, we have to identify certain automorphisms, and then this gives us new VOAs. And we will see that we can construct all of the VOAs on Schelekin's list from the Leech lattice using the correct automorphisms. All right, and the main tool in the proof are vector-valued Eisenstein series. So we already heard yesterday in Sam's talk about certain modular forms, well, vector-valued modular forms are very natural. I mean, are the most natural type of modular form that appears in the context of VOAs, because when you have a VOA, its character is not closed under the modular group, but you have to look at, I mean, let's say a nice VOA, you have to look at all the irreducible modules, and then you look at the characters or the graded dimensions. In fact, you look at the trace function, something more general even, and that, the space that they span, that is closed under transformations of SL to Z, which just means you get a vector-valued modular form, and in fact, you know, it satisfies this congruent subgroup property. So in fact, the individual ones are modular forms, but not for the full modular group, but for gamma n, where n is some level. All right, and in general, vector-valued modular forms are a little bit hard. I mean, there's not really a very good general theory. I think, Terry, you have some notes about this, but here we have a very special case. It's just we have the Weil representation, and that's maybe the best understood case of vector-valued modular forms, where you have a lot of explicit formulae for Fourier expansions and things like this. But this only corresponds to, okay, so we need vector-valued modular forms for the Weil representation. These are special vector-valued modular forms. And the representation, it just means, you know, when you apply your S matrix or T, when you apply S or T, then you somehow act on these characters, and then that means you get a big matrix, and this Weyl representation that tells you what this matrix S and T is. And in fact, you have for every discriminant form. So if you have a lattice, you can look at the dual lattice by its lattice. This is discriminant form. It's just a finite abelian group with a quadratic form on it. Some people call it finite quadratic space or discriminant form. I think Nicolin calls it this way. And whenever you have such a thing and it's non-degenerate, you can attach to it this representation. And the prime examples of such modular forms are theta series. So you have a lattice, you look at you have an even lattice, you have a dual, you look at all the cosets. So these will not be lattices, but they will be cosets of lattices. You look at the theta series, you just count how many vectors are there of which norm, and you write them in a power series. It's just a bookkeeping parameter, but then you realize, okay, they converge to modular forms, and these will transform under the Weyl representation. All right, and so that's the classical example, and then also in the situation of the orbifold theory, you get they transform under the Weyl representation, and that just corresponds to your modular tensor category being pointed. So we have only simple currents. This is exactly the situation where you have your vector value modular form transforms under the Weyl representation. Right? It's more or less if and only if. Yeah? And that's somewhat special, but in the cyclic orbifold for holomorphic UAs, you only have simple currents. Yeah? So these twisted group doubles of the cycle, I mean, they have simple currents. That's all of the irreducibles are simple currents. All right, and so they transform, but however, actually, so they transform under the Weyl representation for a hyperbolic lattice, and because they have weight 0, so that, so they transform under this, if you want to express it, if you want to, this would not have theta series in the classical sense, right? But nonetheless, we can say, because it's a hyperbolic lattice, but nonetheless, we can of course say that some modular form transforms under the corresponding Weyl representation. Okay, so what do we do next? Well, now we want to prove some dimension formula. And a good method in general to get dimension formulas is using some kind of pairing argument where you have some modular forms, vector valued in this case, and you pair them with other vector valued modular forms that transform under the dual representation, then you get a scalar valued modular form under the full modular group, and these are highly constrained, and that gives you constraints on the coefficients. And the coefficients of our modular forms are just dimensions of certain spaces of our vertex algebra. All right, and here we have to use certain vector-valued Eisenstein series. So the general theory of vector-valued Eisenstein series is quite not very well developed, but here we're a little bit lucky. We can start with a scalar Eisenstein series and can lift it. All right, so in general, you should know that the space of modular forms, this is in any kind of classical modular form, vector-valued or not, you can kind of write, and here we're not looking at the full modular group, but we're looking at a finite index subgroup, which is called gamma 0n. So we don't transform under the full modular group, but under some smaller group. But this is true for any kind of, let's say finite index subgroup. The space of modular forms, here we have weight 2. So the space of modular forms but this is also true in other weights, you can decompose into Eisenstein series and cusp forms. And as a direct sum, and actually this is orthogonal with respect to this Peterson scalar product, which is not actually defined on the whole space, but you can at least pair Eisenstein series with cusp forms. So Eisenstein, anyway, so it's an orthogonal direct sum, and you can for many cases you can look at your favorite textbook in modular forms, and it will tell you, what is the dimension of these spaces, and sometimes even they tell you a basis or something like this. I don't know, Miyake or some Diamond Sherman. You can look in these books, and here the number of Eisenstein series typically is related to how many cusps you have in your modular. You take your upper half plane modulo gamma 0n. This gives you a modular curve, and if you want to get to get the modular curve, you have to compactify it. You have to add the cusps, and so the number of cusps you have roughly gives you the number of Eisenstein series. In weight 2, there is a very special thing. You actually get less. You get one less. But this is somewhat special in weight 2. So as many people know, there is no Eisenstein series of weight 2 for the full modular group. If you want it to be, you can either, you could relax modularity, then you get one, or you could relax. So, but you don't have in the classical sense a weight 2 Eisenstein series. You have to say it's a quasi-modular form. but in general, what you have the number of cusps minus 1. You get 1 less. All right, and the dimension of your cusp forms, that's related to the genus of your modular curve. So the x0 here is what I call is the modular curve. And so now we want to look at a certain Eisenstein series, and this is maybe the most symmetric Eisenstein series you can write down for gamma 0 n. Yeah? So you have epsilon many cusps, and you want to now dictate the behavior of your series in the cusp. So you can, for any cusp, you can look at the expansion of your form in the cusp. So I mean, the cusp infinity, which is the normal cusp, you just write down the Q series that gives you the expansion. If you want to get expansion other cusp, you have to apply the modular transformation with a certain matrix MS that moves one cusp to the cusp infinity. In any case, you get expansion in all the different cusps, and we demand that the constant term, this is supposed to be the constant term, in each of the cusps is equal to 1. Okay, and we cannot demand this for all cusps because we have one more cusp than we have degrees of freedom. So we only demand it for all the cusps except for infinity, and then in infinity, the value will be determined, and it's 1 minus the Dedekind psi function, some number theoretic function you don't need to know. And you can actually write it down explicitly, and you see this is this Eisenstein series of weight 2, and you can choose the modular version. It doesn't matter. If you take this linear combination, it will actually become modular and holomorphic, so that's fine. So you can write it down explicitly, and the only thing you should remember from this is it's a very nice and symmetric one. And yeah, so this is the one we have to take, and then we lift it. Again, this is the easiest thing you can do if you don't really know. I mean, vector-valued Eisenstein series, there are explicit constructions, but they are difficult. But in this case, we are lucky. We can just take, we can take this scalar one and lift it. And this lifting, I don't have to write down the formula. I mean, you just have to know. I mean, you basically say what is the 0 component of your vector-valued modular form, and then you get the other components just by demanding that it be modular under, that it be a modular form for the vector-valued modular form, and demanding certain symmetries. So you just fill up all the other components by applying your Weil representation in this thing. So it really the only non-trivial information it has comes from this scalar part somehow. Okay, so we have this vector-valued modular form now, and it will transform. And you have to be a little bit careful how exactly you do this lift. But in this case, we lift it to something that is now modular for this. I mean, we take this, as you remember, the orbifold characters, they were transforming under this Weil representation for this hyperbolic lattice, which has n squared many components in the discriminant form, and we now build something that transforms under the dual Weil representation because we want to do this pairing. So then we do this pairing. So we have the VOA characters, and we pair with this. Vector-valued Eisenstein series. Did I call it F? Yeah. So this capital F is now this vector-valued object that we lifted from this small f, and this will now transform. Now you have a proper vector-valued modular. You have a proper scalar modular form that transforms in the full modular group SL2Z. Yeah? I mean, if you've never seen such arguments before, it might seem a little bit ad hoc, but these kind of pairing arguments are extremely powerful. Yeah? And they're used in many situations when people study modular forms. Yeah? And now what you do is you just use the residue theorem now, and it tells you the constant term, because this is holomorphic on all of the upper half plane, and the only possible pole it can have is at infinity. In fact, it must have a pole at infinity, otherwise it would be trivial, constant. And the residue theorem tells you then that the constant term must vanish. That's just the residue theorem on this the Riemann sphere. Now we are for SL2Z, so the corresponding modular curve is just a Riemann sphere. And then moreover, we have to use, and this is then pages of explicit tedious computations, but unfortunately you have to go through it. And then, so now we get whenever you do this, I mean, this is nice. So you take any VOA character, you take some VOA stuff, and you can pair with anything you like. You will get non-trivial identities. Yeah? There will identities amongst the different coefficients that appear in your modular form, or in other words, amongst the dimensions of certain weight spaces of your modules. You can do this, you always get some non-trivial identity. It's just you have to identify the cases in which they are interesting to you. All right, and in this case, with this choice of modular form, and you can do other choices, and we discussed this a little bit also in the paper, you can get other constraints, but with this special choice of Eisenstein series, you get this dimension formula, which is kind of the main result here. So we want to understand this orbifold construction. So we start with this VOAV, and we take an automorphism of some order, and we look at the corresponding orbifold construction. And actually, we want to know what is the dimension of the weight 1 space. The character of this must be the J function plus some constant. So the only unknown in the character of a holomorphic VOA of central charge 24 is the constant, is the constant term which corresponds to the weight 1 space. All of the other dimensions you already know because it must be the J function. So that's the only one you don't know. And here we have this nice dimension formula that tells you, okay, it's 24 plus some, these are these coefficients I mentioned in the beginning, plus some linear combinations of this is your original VOA, and you look at the fixed points under powers of your automorphism. And then you have some rest term. And the rest term contains everything that's ugly, and that we cannot compute explicitly. But because this part here, it's super nice to compute. I mean, you know your automorphism, you know how it acts on your VOA. What you don't know necessarily is how it precisely acts on the twisted modules and all of that stuff that enters the orbifold construction. That's very hard, but we don't need to know this here because all of this is just the action on the VOA itself, and that's basically by definition of your automorphism, you know what this is. And all the difficult part is the rest term, and by some miracle, you can prove that this rest term is actually non-negative. So the coefficients that appear in this rest term, and this has to do with the very, very special choice of Eisenstein series, are non-negative, and then because they are just linear combinations of dimensions, it will be a non-negative number. Yeah? And that gives you an upper bound for this dimension of the orbital construction in terms of something very easy to compute. And moreover, this stuff this term that's written here also appears in this very strange formula by Katz, from a completely different context, but somehow it appears. And so then we just naively, I mean, of course, it wasn't that naive, but we have this upper bound, and then we just say, okay, let's call an automorphism extremal if it satisfies this upper bound coming from this modularity. And then, so that's and these automorphisms that satisfy this upper bound turn out to be quite important. All right, and this leads me to the conclusion where we use all of this to the classification. Yeah? So then based on this notion of extremal automorphism, we define generalized deep holes. Why they are called generalized deep holes, I will tell you after I tell you the definition. So the definition here is just you take an automorphism of the of any holomorphic VOA of central charge 24, and it has to be extremal, and then we have extremality is like a condition on the dimension, and then we have also a dimension on the ranks of these Lie algebras. So that tells you in a sense that you go to the fixed points, you get your rank in general becomes smaller. You start with some rank, you get to the fixed point, the rank might become smaller, and we say here, when you go back up, the rank should not increase anymore. And, well, with that definition at hand, we have, at the point when we made this definition, there are already two cases that this definition applies to. First of all, if you take just the ordinary deep holes of your Leech lattice, this is the old business, and you make them into automorphisms, they will give you constructions on the vertex algebra level now of the Niemeyer lattice vertex algebras. So you replicate this lattice construction on the level of vertex algebras. Moreover, all of the constructions of the moonshine modules turn out to also satisfy this definition. They're also extremal. And that was a little bit more surprising and kind of made us think that this maybe is the correct definition. Yeah? So Carnahan, and maybe I should say also Michael Truitt a long time ago, they had this idea so originally, of course, the moonshine module was constructed by an orbifold of order 2 from the Leech lattice, and you can actually do it. This is not, the number 2 here is not special. Yeah? You can construct it in many, many different ways from the Leech lattice. In fact, there's a 51, or I usually say 38, depends on how you count, constructions from the moonshine module. And they're all none of them is better than the other. And they are automorphisms of different order, and they have trivial fixed point lattice. So in that case, you start with the Leech lattice, then you go to something that has rank 0. Your Lie algebra is rank 0, and it doesn't increase anymore because you get no contribution from the twisted modules. So you stay at something that has, you know that the answer must be a vertex algebra that has vanishing weight 1 space, and the hard part is to prove, and that is what Kanahan did recently, is to prove that you actually always get the Moonshine module. And then this definition in this case is relatively easy to verify, this extremality. You see that all of them are extremal. So all of them are examples of generalized dipoles. But then actually this is not what we want to do. We want to construct all of the ones that are not the Moonshine module. But nonetheless, even the Moonshine module constructions fit very nicely into the picture of this definition. And then using this Katz's Lie theoretic very strange formula, so we use our dimensional formula, and we can combine it with this very strange formula to get a new formula, which then very conceptually lets you prove this bijection. So we get a bijection which is mediated by the orbifold construction. So you take the Leech lattice VOA now. So now you can do, generalized dipoles exist for all the VOAs that have central charge 24 and are holomorphic, but now we only look at the Leech lattice VOA. And we take a generalized dipole, and we look at the corresponding, and we take the ones where the rank of the fixed point lattice is where you have non-trivial fixed point lattice, or the rank of the fixed point VOA is greater than 0, because otherwise you'd get the Moonshine module. And then you actually get a one-to-one correspondence between these generalized dipoles and the vertex algebras on Schelekin's list with non-trivial weight 1 space. And this is proved abstractly without classifying either side. So this corresponds to this result by Borcherds. Yeah? So here we have not used any classification at all, and you get this one-to-one correspondence. And then, yeah, so that's the result. And as I said, 90% of the proof is, in the end, is modular forms. It's really using very kind of, highly symmetric Eisenstein series, and anyway. So, and it generalizes both this original construction of the Niemeyer lattices from the Leech lattice, and it also generalizes or it also encompasses the construction of the Moonshine module. Okay. All right, and just have to say, in this case, you don't get a one-to-one correspondence, right? You get a one-to-one correspondence in the case where you have non-trivial fixed point lattice, or where you have non-trivial weight 1 Lie algebra. There it's 1-to-1, and for the Moonshine module, it's 51-to-1 or 38-to-1. Yeah? Slightly different behavior. And then, of course, in a sense, because these VOAs were already classified using more ad hoc methods, we already, basically from this one-to-one correspondence, we get a classification of the generalized dipoles, but of course we want to do it the other way around. We want to give a very simple classification of these VOAs. This was over many, hundreds of pages of papers. We want to give a very short and concise proof that uses this one-to-one correspondence. Yeah? So now we want to actually just classify these generalized dipoles in the Leech lattice using like lattice methods in a sense. And well, that's the classification of these generalized dipoles, right? So you get 70 generalized dipoles where the rank of this fixed point vertex algebra is greater than 0, and they correspond in a one-to-one way then to these cases on Schelekin's list that have non-trivial weight 1 Lie algebra, and then you have 38 classes that give the Moonshine module, and I said the 51 comes from counting in a slightly different way. All right, and now let me tell you in the last 5 minutes, and this is the new result that we just put on the archive a couple of months ago. How do we classify this? And this is kind of a geometric. This is along the lines of how Conway, Parker, and Sloan classified the dipoles. So but you have to generalize these notions in a kind of correct way. So to a hole in a lattice, you can look at, so if you have a hole in the lattice, it's maximally away from the lattice, but then you look at all the points in the lattice that have this distance. Yeah? And if lattice is 24-dimensional, it must be at least 25 points. Otherwise, it wouldn't be a hole. You could move it slightly more to get more. And these points between 25 and 48, in the case of the ordinary holes for the Leech lattice, they form a diagram. you connect you connect them by edges following a certain rule, and this gives you actually an affine Dünken diagram. And then you just have to classify. You forget about holes, and you just classify the affine Dünken diagrams you can find inside a lattice. And well, you can now you just have to generalize this in the correct way. So now we're not going to look at the Leech lattice anymore, but at projections of the Leech lattice along some automorphisms of the automorphism group of the Leech lattice. And then you have to find in these projected lattices, which come from the Leech lattice, but they're projected down to smaller rank, you find there, so the generalized dipoles again correspond to certain points in these lattices. And you again have to classify what are the possible diagrams that can occur for these points. And then you just classify these diagrams, and this is a relatively manageable computation, and that gives you a classification of the generalized dipoles. Yeah? All right, and so we classify these diagrams, we classify the corresponding generalized dipoles, and just to give you an example, yeah, what this means. So here we have the lattice A2. This is not an actual example in the computation, but it's the only lattice you can draw, essentially. That's not one-dimensional. And this is the lattice A2. You could find, for example, the diagram A1. So the red point would be your hole, which is not a dipole in this case, but it doesn't matter. I mean, here would have the closest point is just this point. This is just one point. It's A1. If you have this one here, you have 2 points, which are the closest ones. This gives you A1 tilde as a diagram, and if you have such a point, you would get A2 tilde. Yeah. So in the more general setting here, we can get affine and non-affine diagrams. Okay. So the problem you have to solve is just find what are the possible diagrams you can find in these lattices. That's the problem in the end you have to solve. And then you get the classification of the generalized dipoles, and that way we recover the classification of the vertex algebras in central charge 24. Yeah? And then we can, this is not, I mean, this is a very nice result, I find. It's not completely the end of the story. Then you can kind of ask yourself, how is this related to other constructions, other uniform constructions? And I think now we understand, I mean, Höhn gave a different kind of approach, and I think we can kind of try to understand how this is related. But I mean, the takeaway here is that now these VOAs, these 71, let's say 70 VOAs, they're not completely sporadic, but they fall into 11 families. And these families are indexed by certain elements of Conway 0, of the automorphism group of the Leech lattice. And recently also Chiral and Miyamoto gave a different proof that's still based on orbifold construction, but they try to go to this hyperbolic setting, where you then end up in central charge 26. But all of these results in the end recover this nice structure that now these 70 VOAs fall into these 11 families, and we can see this very nicely on the level of these generalized dipoles. Yeah? And these are these families. So you have from A to K, this is 11 families, and L would be kind of the special case of the Moonshine module, which is slightly a little bit different. And you can see, which is very nice now, so these are the cycle types. So these describe how your automorphism acts on the complexification of your lattice, or on the ambient vector space. If you've never seen this before, never mind, but if you know what they mean, you see that they are very highly symmetric. And then, so this is kind of determines, so the automorphism group of a vertex algebra in general is kind of a difficult object, but it's kind of always has this Lie type, and it has then some finite, and if you divide by this inner automorphisms, which are some kind of Lie type group, you get some finite group. And in this case, the order automorphism group is exactly this automorphism group of the lattice. In general, will not be. This is special for the Leech lattice. So this kind of tells you what is the outer automorphism, and then we have some inner, and these different orders come because you choose different inner automorphisms. Yeah? So you have different orders, and then if you fix one of these families, your dimensions will lie on linear trajectories. Yeah? So the rank will be fixed for each family, and then your dimension will always be some linear trajectory. Yeah? So you have a somewhat nice or at least it doesn't look completely sporadic anymore. Yeah? And then finally, 1 minute left maybe, what am I working on currently? So how can you, well, you've classified now the holomorphic vertex algebras, but of course people are also interested in holomorphic vertex super algebras. Yeah? And well, then you remember how was this done for lattices, and how did, and Borchards, yeah, I mean, this is it's sideways, otherwise it wouldn't fit. And so how do you classify odd lattices? Yeah? Well, the best way to do it is maybe how Borchards did it. He looked at the neighborhood graph, and you realize that, so all of these nodes here are Niemeyer lattices. There are 24 nodes here, and then you realize that an order 2 neighborhood relation actually gives you an odd unimodular lattice. And there's a one-to-one correspondence between odd unimodular lattices and the edges in the 2 neighborhood graph. Well, you can guess what? You can do the same thing for vertex operator algebras. So if you take it as 2 neighborhood, you take the order 2 orbifold construction. Any edge in your order 2 neighborhood graph for the holomorphic VOAs will now correspond to a holomorphic vertex operator superalgebra with correct statistics, right? So where the even part is Z graded and the odd part is Z plus 1/2 graded. That's the case you study here, and you know, we started to investigate this, and now your graph will have 71 or let's say 70 nodes and many more edges. And I mean, we're not completely finished with this, but it looks like there are about 1,000 holomorphic vertex superalgebras. Yeah, and that's so once you have the classification of the VOAs, it's very natural then afterwards to consider the classification of vertex superalgebras. Yeah, yeah, and I think that's where I end.
Thank you. Are there questions or comments in the audience or on Zoom? Oh yeah, there is a question there.
Hello. Maybe it's a stupid question, but do we have analogous results for other numbers than 24?
That's a very good question. No. There are several problems here. So the first problem is that if you go to, I mean, okay, rank 8 and central charge 8 and 16 is you know, very trivial in a sense, and then you have the next one is 24, where it's somehow manageable. And then even if you just look at the lattices for higher rank, it becomes too big. So we only have, for example, for lattices in rank 32, we know that there is a lower bound of about 10 billion, I think. And this is just the lattice cases. Yeah? Then you have to think, what can you do? I mean, it's completely hopeless to get a classification in this case, right? And what some people do is, however, they study certain special VOAs that are called extremal VOAs, yeah? Where the characters are in a certain sense extremal, and the Moonshine module would be an example of an extremal VOA. And they are, Gemünden and Keller, for example, have some papers, have 2 papers on this, where they try to find these extremal VOAs in higher central charges. So you can look at some subproblem, but you cannot get a complete classification. And also, everything that was done here from this pairing argument is very particular to central charge 24, because once you have, so here, you know, the central charge corresponds to the pole in your modular form. And here we have a pole of order 1 at infinity. If you go to higher central charge, because of this q minus c over 24, you get bigger poles. That means you get many, many more terms in your formula, and we will not be, I'm very sure we will not be able to find a nice bound form like this. So I think that's really, none of this works in other central charge.
Okay, are there other questions? Or observations? comments? Okay, well, if not, let's thank Sven again, and we can also talk with him later.